Let's talk about a cipher called the one-time pad. This is actually our first example of a secure cipher. We will also look at why this is secure and what are the pitfalls of such a secure technology. To demonstrate the one-time pad, we will use binary strings, so strings of ones and zeros, as the messages, ciphertext, and keys, just to illustrate the process a little better, and also because, well, computers process data in binary format anyway. So for the one-time pad, an acceptable message could be, for example, any binary digit string. Let's say it's going to be 010101. A valid key might be 101010, and a ciphertext will come back to how a ciphertext would be formed from this message and this key. One-time pad does have one requirement though. The key should be a random bit string that is as long as the message. The encryption algorithm for the one-time pad is very simple. It uses the key and message and calculates the exclusive OR operation for these bit strings. As an example, we have here a string of bits. So if we look at this example here, we start to calculate the exclusive OR operation. So for 0 and 1, the resulting exclusive OR bit is 1. For 1 and 0, it's 1. 1 and 1, it's a 0. 0 and 1 results to 1. 1 and 0 is 1. 1 and 0 is 1. And 1 and 1 is again a 0. The decryption algorithm is, well, it's the same operation, this time just using the key and the ciphertext. So for instance, here, starting from the left of the ciphertext, 1 and 1 XOR together produces a 0, 1 and 0 produces a 1, 0 and 1 produces a 1, 1 and 1 produces a 0, 1 and 0 is 1, 1 and 0 is 1, 0 and 1 is 1. And at the end, the resulting deciphered message should match the plain text message that we started out with. So because the encryption and decryption algorithms are so simple, the one-time pad is actually very, very fast. The downside is that we require very long keys because we need to have as long a key as we have the length of the plain text message. The one-time pad is an actual real cipher, and many stream ciphers that we will talk about later actually are based on the ideas of the one-time pad. Now let's see if we can say something about the security of the one-time pad. Is one-time pad secure? What even is a secure cipher? And if one-time pad is secure, can it be otherwise problematic? Let's start with the question of what is a secure cipher. So let's think about, what does a potential attacker actually see? What are the abilities of eavesdroppers or potential attackers? So often they can listen in to the data streams, the traffic, meaning they can get hold of the ciphertexts. So we might have some security requirements like this, like attackers should not be able to recover the key that was used to encrypt the data, and the attacker should not be able to recover the plain text messages. In information theory and in cryptography in general, there is a very important rule of thumb. This is that a ciphertext should never reveal any information about the plain text messages. Secrecy based on information theory was codified by Claude Shannon already in 1949. Based on information theory, we can say that an encryption or a cipher suite over the key space, the message space, and ciphertext space is perfect given the following conditions. For all messages that are of the same length, the probability of a certain ciphertext being the result of the encryption and the probability of any other message encrypted using the same key should be the same. So when we pick a message at random using the same key, it should be equally probable for the ciphertext C to be the ciphertext here. And also we presume here that the key has been selected at random from the key space and the key space is uniformly distributed. So in practice, if we select a random message and a random key and end up with a ciphertext that is something, let's say it's 101010 and so on and so on, the probability that this happens to be the ciphertext should be equal for all possible messages that we could possibly want to encrypt. So the probability that it's this particular ciphertext should be the same across all messages and all keys. So why is it important that the probability for a certain ciphertext to appear from the encryption algorithm for all possible messages? Well, this means that if we look at a ciphertext, a possible attacker cannot possibly tell if the original message was or what the original message was, because the probability for all the possible input messages is the same. So even the most powerful attacker doesn't learn anything just by looking at the ciphertext. This actually only means that there is no possibility for a ciphertext-only attack. Of course, other attacks are possible, but this is the foundational rule for secrecy, perfect secrecy based on information theory. Next, let's evaluate if the one-time pad is actually a perfect cipher. So let's consider how many keys map all of the possible messages that we could try to encrypt to a particular ciphertext. So here, the lowercase k is a randomly selected key, lowercase m is a randomly selected message, lowercase c is the resulting ciphertext, and the uppercase K is the number of keys in the universe for all possible keys. So since the key in one-time pad is always as long as the message itself, there is always exactly one key that maps a particular message to a particular ciphertext. So that means in practice that this encryption using the one-time pad actually achieves perfect secrecy. What this means in practice, let's consider, for example, a message that reads one-time pad, and then we have a randomly selected key. You will notice I have moved from binary messages to text-based messages, just for the sake of the demonstration. Anyway, if we do the exclusive OR operation using bit strings generated from from these messages, we would end up with a ciphertext like this. Now, why does the one-time pad achieve perfect secrecy? Well, this given ciphertext could produce any message that has the same length. If we used this as the key, the deciphered message would read salmon egg instead of one-time pad. Or if we used another key, another possible key, the deciphered message would read green fluid instead of one-time pad. So just by guessing what the key is doesn't reveal anything from the original message, and this is what makes one-time pad a perfectly secure cipher. In general, what Claude Shannon's theorem actually says is that encryption is perfect, or the encryption achieves perfect secrecy, if the length of the key used to encrypt is as long or longer than the length of the message. The bad news here is that this is really hard to use in practice, even though there are or there were real-life applications that did use the one-time pad as an encryption mechanism.